It's tempting to think and fall into the trap of the universe as something that is inherently explainable through mundane means. It's not always that clean cut. When you plug in your phone and charge it, electrons are transferring. That is electricity, and it's very predictable. But that is a kind of false sense of security because our universe, just under the crust of the normal, is very strange indeed. Indeed, in some respects in physics, the universe almost appears illusory, a proxy as we see it for the quantum realm, where even things like locality, being in one place without jumping instantly to another, fall to the wayside. This is the source of such things as the ambiguity of the interior of black holes, where whatever happens in there is effectively no longer part of this universe, as framed by Stephen Hawking, and why general relativity, the great predictor of what we see on our size scales, falls apart when one tries to apply it to the quantum world. Einstein himself was vexed by that, and spent the latter half, actually the greater part, of his career trying to tackle to no avail, especially in regards to a quantum theory of gravity, which we still do not have. But general relativity really was an exercise in thinking outside of the box. Special relativity, not so much. There were other scientists at the time circling the drain on that one, but general relativity came out of seemingly nowhere to explain apparent discrepancies in the science of Newton. It is actually possible that had Einstein not come along, we may still to this day not have general relativity. But general and special relativity do not describe everything. They merely approach certain points about the universe, one of which is time. Time to us is time. It is the ticking of the clock. But that's a construct of our own making. But there is in some sense some kind of actual time given relativity's prediction, well proven, that time dilates and ticks at different rates in different areas of the universe depending on acceleration and gravity. But in the end, there have been other outside-of-the-box ideas advanced in physics over the decades that we still do not have enough information to either confirm or deny. One such idea was advanced by theoretical physicist John Archibald Wheeler in a phone call to Richard Feynman in 1940. Wheeler was famous for these kinds of off-the-wall theories in physics that, just maybe, actually describe reality. In this case, the postulate he presented to Feynman was the one electron universe, and that all electrons, and their antimatter counterparts, the positrons, are actually an illusory manifestation of the same electron moving forward and backward in time, changing direction, and we see that as our multitude of electrons and positrons in our time frame, when that is an illusion and it's all the same one. What prompted Wheeler was puzzlement over why all electrons have exactly, very exactly, the same charge and mass. You could say that might be because all electrons must be the same, but what imposes that rule? But another take is that they are quite simply all the same electron, and when it moves backward in time, it appears as a positron. And Wheeler wasn't alone. There was another scientist, Ernst Stueckelberg, who was thinking along the same lines of a zigzag world line for how particles and antiparticles annihilate. Ultimately, this meant that antimatter was in fact anti-time. While not much ever came of Wheeler's one-electron universe, most physicists do not think it is the case, it did spur Feynman into thinking more broadly about antimatter being a representation of matter moving backwards in time, called the path integral formulation, and a spacetime interpretation of quantum mechanics, something that netted him a Nobel Prize in 1965. Not bad for ideas spawned from a seemingly crazy out-of-the-box idea. Electrons can be diverted. Photons hit them and they can wobble around. But turning completely around and heading backwards in time is a different animal altogether. But it pays to remember that by imposing time here, there is a caveat. It is not necessarily that the electron really is traveling backwards in time, though that is a possibility. It's more that the difference in charge between an electron and a positron, matter and antimatter counterparts, is physically indistinguishable from if they really were time traveling. But they really have just reversed charges. But if they are all the same particle, it means it's time traveling backwards for a positron. However, we do know one thing here, and that is that the electron is indeed time traveling, like everything we see around us, including yourself. We are forever moving forward in time, and that rate, as relativity shows, can change. You can travel to the future much faster in this universe than you currently are by going fast, or sitting next to a black hole, one of the better plot points of the movie Interstellar, though the nuts and bolts of that black hole is a bit more complicated in reality than portrayed. Indeed, you can take this so far as to say that whenever you see a positron and an electron annihilate, they actually aren't doing that. It's that it's simply the electron being deflected back in time by changing direction. What that means for other forms of antimatter is an open question, a very tricky one. But it does have another implication, that energy can move backwards in time. But it actually can't. That violates entropy. So again, it's all very uncertain what this means, and may boil down to an expression that makes physics simpler for mathematicians. The real problem with the one-electron universe idea is that it implies that we should see about the same amount of electrons as we do positrons in the universe, and we don't. We see orders of magnitude more electrons than positrons. Indeed, there are deep mysteries about positrons in the universe that don't make a lot of sense in this context. Perhaps the biggest one being the existence of antimatter fountains of unknown origin in the Milky Way that spew enormous quantities of positrons out that travel for light years until they hit something and annihilate. These apocalyptic zones are somewhat a forgotten area of astronomy. They were discovered starting in 1997 with the Compton Gamma Ray Observatory. The one it discovered is coming roughly out of the galactic center, extending out for as much as 3,500 light years, and that huge mess of annihilation causes gamma ray emissions. This is a lot of positrons, 10 million trillion trillion each second. This means that in just a few seconds, several 100 billion tons of positrons and normal matter is annihilating in the Milky Way's central bulge area. It's all simply disappearing in a puff of energy. But when you look for a source of this activity with a telescope, there is nothing there. One idea at the time was that they actually are legacy positrons, millions of years old, from a time when the Milky Way's core was more active, and they just haven't encountered anything in the vacuum yet. Or it might be something neutron stars or an unseen black hole are doing. But you'd think we'd see that everywhere with those environments, and we don't. And it's sort of a double mystery, and not only are the positrons unexplained, but whatever is hurling them through space is also not evident. More intriguing perhaps is that the positron creation might be some kind of an effect of dark matter. And since we don't know what dark matter is, we don't know what the interactions it has with itself are. But the one-electron universe wasn't the only outside-of-the-box idea Wheeler had. In addition to a mountain of work in physics in general, he also asked the question, how does something come from nothing, as the universe appears to be doing? This led him to formulate what is known as the participatory anthropic principle, which is based on the notion that information is fundamental to the physics of the universe. In other words, all physical objects simply represent information. He called it "it from bit," in that everything in the universe, directly or indirectly, comes from binary choices, yes or no questions, like a computer, and that reality emerges from this. In a sense, that's not unlike seeing it all as a computer program. But in this case, we are participating in the program. This is unusual stuff that Wheeler realized after a thought experiment, that the questions we choose to ask about the universe may be dictating the answers we get. To put it another way, the questioner doesn't decide anything beforehand, but only on a pattern of questions with yes or no answers. The succession of the questions requires narrowing down the options for answers as they are asked, even if those answers in the universe are true, ultimately meaning that consciousness, in Wheeler's interpretation, seems to play a role in bringing reality into existence. Wheeler felt this acts retrocausally, in that we also, through this mechanism, are bringing about the now and close, but also the distant, past. The future presumably remains unwritten. In short, consciousness, meaning us and any aliens out there, are what makes the universe manifest, and if there were no one here, the universe would not be here either. In short, in this framework, everything really is an illusion. While I do not buy this interpretation myself, I think the universe probably has a way to be here even if we aren't looking at it. The idea does come from Wheeler and several other luminaries in physics, and at least gives us food for thought on this, at least for me, cool, spooky season evening. Thanks for listening. I am futurist and science fiction author John Michael Godier, currently adding in another aspect. There is the idea that, like quantum particles, the universe itself has a wave function, and in this sense, something has to collapse it for it to be here, which again could be consciousness, or maybe something else. Very strange stuff, and be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.